Good morning, everyone. Welcome back to modeling of low frequency control systems. In the last lecture, we have seen the modeling of speed governor system. In today's class, we will look into the modeling of the other components of low frequency control of a single area. So now we will be discussing the modeling of a steam turbine. Turbine, as you know, is a device which takes in steam input So hot steam will be onto the turbine shaft. It will be onto the turbine. And it rotates based upon the energy which it receives from the strong injet of steam. So as a result, it will be rotating. So the output can be considered as mechanical power. So the output is going to be the mechanical power. So now we will be trying to model this turbine with an input of steam valve setting. So I'm considering the input as steam valve setting and the output as a mechanical power. Now, moving ahead, now shown in the figure is a two-stage steam turbine. It is a two-stage steam turbine which is generally employed. Now, in this one, if you carefully see, there is stage 1 and stage 2. And from stage 1 to stage 2, apart from this one, we will be having a preheater also. This is a representation of a two-stage steam turbine, where you will be having a steam valve here. This entire thing is considered to be the steam valve. From steam valve, you will be getting this input as a delta YE. Now this is being given to stage 1, and stage 1 again it will be given to stage 2. Apart from this, you will be getting some extra preheating arrangement. You might have seen in the thermal plant preheater. So here, from here, the steam hits the turbine, and this turbine is going to deliver you mechanical power, which will be transferred to your generator. So on a whole, if you see this turbine, the dynamics, how it responds, are function of, or two things primarily. The first thing is the steam between the inlet steam valve and the first stage of the turbine. This is steam valve. This is the steam valve. Okay. So between the steam valve and the turbine. So whatever the steam which is coming from the steam valve to the turbine, this is gonna influence the dynamics of your turbine. The higher the steam input, the higher will be the mechanical power output. Okay. Now the second one is the preheater. If you carefully see, I have considered a two-stage turbine. Normally, you can consider a single-stage turbine also. What is the function of a preheater? Preheater is just like a storage element. So it gives you a storage action, which causes the output of the low pressure. See, the first stage is the first one is the sorry. The first one is the high pressure steam, the other one is the low pressure steam. Now, this preheater basically, which is considered as your storage element, it causes the output of the low pressure steam to lag behind the high pressure steam. So normally, since you are employing two stages, the turbine transfer function is characterized by two time constants, one for the LP stage, one for the HP stage. If we consider a single stage turbine, then we will be having only a single time constant. But whatever may be the number of stages which you will be accounting for ease of our calculation, we will assume that the turbine is assumed, we are going to assume that the turbine is going to have a single time constant. A single equivalent time constant. Normally, this time constant will be having a range of 0.2 to 0.25 seconds. So whatever may be the number of stages which you are employing here, this is a reheater. Whatever the number of stages, each stage will be having a different time constant. So even though it is having many stages, for ease of calculations at the UG level, I am considering a single time constant, and I am representing a total, which is nothing but the time constant of your turbine, and KT represents the gain of the turbine. KT represents the gain of the turbine. So combining all stages, assuming that there is only single time constant. Normally, a steam turbine is designed such that it has a time constant of 2 to 2.5 seconds. 2 to 2.5 seconds. The gain, KT, this is time constant, okay? Total. KT is designed such that earlier we used to have speed governor, right? KSG, this was the gain of the speed governor. KT is designed such that KSG into KT will be approximately equal to 1. So normally, if I use KSG as 2, I'll say KT as nearly 0.5 or 0.45 like that. So in our present case, in order to understand the dynamics of the system, so I'm considering KT as 0.45 and TOT as 2. Okay. Now the model, transfer function model for this one is going to be KT by 1 plus S total. The input is going to be delta YE of S, which is coming from the speed governor. The output is delta PT of S. In some textbooks, it is also referred to as delta PM of S, which is M represents the mechanical power. So once again, repeating, this is a single two-stage turbine, steam turbine, where it consists of two stages. One is a high pressure stage, the other one is a low pressure stage. Apart from this, there is a storage element, the reheater, which generally causes the output of this one to lag behind this HP stage. Overall, what is its purpose is nothing but it is going to give you a mechanical power, which will be given to your generator to run the motor, to run the rotor. Now there is only one input to this entire one, and that input is your steam valve setting. So the steam valve setting is going to govern the amount of mechanical power which you are employing. Internal, whatever number of stages which you do, it will just control the total overall time constant and overall gain. So for ease of analysis, I'm combining this entire one into a single time constant and a single gain, and I'm representing this fashion. This is the input and this is the output. Now, having said this, now let's get back to our MATLAB model, where we will be seeing how this time constant and the gain are going to affect this mechanism. Okay. Now, I'm gonna take off this one. See, once again, remember the gain I'm choosing as 0.45 and the time constant I'm choosing as 2. Now let's get back to our MATLAB simulation model. Okay. This is a commonly used blocks, or you can find in the sources. You can use this constant. And apart from this, I need a transfer function block where I can find it in the continuous section. This is this one. And apart from this, I do need a scope. You can find it in the sinks. Now, if you carefully see, this is my this one. This is YE setting, isn't it? YE of S. And as I told you already, time constant, I am choosing it as 0.45 and the gain is 0.45. Time constant, I am choosing it as 2. Now the output is input is YE of S, right? I hope you are able to see this one. I want to see the output and input simultaneously. I'm trying to include the input signal also. The scope and layout I'm adjusting. This is the input and this is the okay. Now let's get back to the simulation. I'll run it just for 0.5 seconds. This is the input. I have given it as 1 per unit. Now let us run it for 10 seconds. Let's see whether, see, this is the change in steam setting and this is the change in the mechanical. Okay. Now let's see if there is a 100% change. I've given it as 1. See, there is nearly 40% change in the mechanical. Isn't it? It is trying to settle down at see, nearly 8 seconds, and the maximum value is going to be 0.4, which means 40% of the net mechanical power. Now let's see what is the impact of the time constant. This is the time constant, right? If I keep it as 5, let's see what is the effect of this one on the output. Earlier the settling time was 8 seconds. The output at 40. See, even at 8 seconds, it is still increasing. Now let's try to run it for a larger time. See, it's settling down at 20 seconds. If you vary the time constant, the settling time is going to vary. See, the peak is still at 0.4 itself, 40% or 42%. But see, the settling time is going to vary. Okay, that is the impact of time constant. Now, at 2, I got it at 8 seconds, right? I'll show you again. At nearly 8 seconds, I am getting it settling down. The peak is at 0.4. Now, I'm going to vary the gain now. Okay, see? Instead of 0.45, I'll take this 0.8. See, the settling time remains at 8 seconds. But see the peak value? There is an 80% change in the mechanical. Understood? Now, for 100% change in the steam setting, there is an 80% change in the mechanical.